Okay, so I'll just start, I guess. I'll see if this works. Okay, so right, already did the introduction stuff. Basically, I was going to talk about dark matter, what it is, how we know about it, what we can learn by observations, and so on. And I was going to start with just sort of briefly mentioning sort of who I am, where I come from, how I got to be in cosmology, just to give you a little bit of background. So cosmology is the big questions. It's the questions of what is the nature of the universe, what are the components of the universe, where does it all come from, how does it begin, how will it end, all that kind of thing. Um, and the way you get into it is in my case anyway, you do the academic career track. If I was able to actually do these slides, it would be all nicely animated and stuff, but anyway. So usually the way it goes is you do university and then postgrad, and depending on where you are, postgraduate research or postgraduate training. Grad school is something like 4 to 6 years, and then you do postdocs. That's the stage I'm currently in. You do a research fellowship somewhere, and it can be between each postdoctoral fellowship can be something like 1 to 3 years. And you do as many of those as you need to until you can get a faculty job. Usually the standard thing these days is to do 2 postdoctoral fellowships and then apply for faculty jobs. And then you do faculty, you do sort of the junior stage of that for up to 7 years, and then you hopefully, if you're very lucky, get some kind of lifetime faculty position, i.e. tenure. So there are a number of perks to this kind of job. Mainly, travel is a really big one. You go all over the world because cosmology is a very international field, and you get some really cool intellectual freedom in the sense that you get to basically work on whatever you want, whatever sounds interesting to you, and that's what I'm doing. I'm currently on a fellowship where I wrote a research proposal and sent it to the Australian government, and they said go for it. And it's kind of just what I think is interesting. So that's a fun thing. That's a really nice perk to the job, and you get to be a cosmologist, and that's kind of the coolest thing I think is possible to do with one's life. Obviously, I think that because that's what I'm doing, but I get to study the universe, and that's like my job. So my career path, I guess, was already kind of outlined. I started out in Long Beach, California. Went to Caltech for undergrad, Princeton for grad school. My first postdoc was at Cambridge, and my second postdoc that I'm doing now is at the University of Melbourne. And I'm about a year into that. I've got 2 more years on my contract. And from here, I basically need to get a faculty job. So that's the path that I'm on. I mentioned travel. This is a map of the places that I have traveled for science. The sort of blue pinpoints are places that I did sort of extended research. The light blue, I don't know, teardrop shapes are places I've been for conferences or collaboration visits or to give talks or whatever. And the key thing is that all of that travel is work travel that is sort of funded by my grant or some university somewhere. So that's kind of a big perk, that you actually get to do a lot of travel and you don't have to pay for it usually, because the government pays for it, or some government or some university, and that's very convenient. So I started on the west coast of the U.S. And I've been traveling east since then. So if that trend continues, I should be in Hawaii or back in the U.S. next time. We'll see. So I'm going to talk about dark matter. Dark matter is what I work on, and dark matter comprises something like 27% of the universe. Most of the matter in the universe is dark matter. I'll explain in a bit what exactly dark matter means as opposed to regular matter. Um, a huge chunk of the universe is dark energy, and I don't have time to explain that at all. And that's okay, because we know virtually nothing about dark energy, aside from that it's really, really weird, and it's making the universe expand faster, and I could talk about that later if you're interested, but yeah, that's even more of a mystery. So what we know about dark matter is that the majority of the matter in the universe is invisible. We think that dark matter is, well, so some of these things we know really well and some of them we know less well, but basically dark matter is massive in the sense that it has gravity, it attracts and clusters, it's cold in the sense that it's slow moving, it's collisionless in the sense that it's sort of this ghostly stuff that passes through itself and passes through other matter. It's invisible. It's not dark in the sense that, like, normally a dark thing is something that absorbs light. Dark matter doesn't absorb light at all. It also doesn't emit light. It's really, truly invisible. And it's non or weakly interacting, so it doesn't have any confirmed non-gravitational interactions with other particles. Basically, the only thing we know that it does is gravitate. It doesn't seem to have interactions with other particles with any other force. What we don't know is we don't know the fundamental nature of dark matter. We don't know how it formed in the early universe. We don't know whether there really are any other interactions, or if they're just too weak for us to see. And we don't know whether dark matter interacts with itself by anything other than gravity. And these are all things we're trying to figure out. So how do you look for something that's invisible? Basically, since all we have with dark matter is gravity, we look for evidence of the gravitational pull of dark matter. And this image is somebody swirling around light sticks in the dark, and if you look really carefully, you can see that there's a person in there. But if you just see that light, you would infer that there is somebody in there swirling something around, because things don't just fly around in circles on their own. And that's basically the principle behind how we see where dark matter is that we see things moving around in ways that they couldn't possibly do unless there was something pulling on them, something using gravity to move them. So one of the first people to, actually I think, yeah, better slide for that. One of the first people to think about dark matter was a scientist called Vera Rubin in the 1970s. And she was looking at how galaxies rotate. And basically, if a galaxy is rotating, if it's like kind of on edge or something, the part of the galaxy that's moving toward you is going to be blue shifted, and the part of the galaxy that's moving away from you is going to be red shifted. Blue shift and red shift are a kind of Doppler shift of light, where something that's moving toward you looks bluer, its light is shifted into the higher frequency part of the spectrum, and something that's moving away from you looks redder, its light is shifted into the lower frequency part of the spectrum. And you can do that with galaxies. Usually you look at the gas in the galaxy and you measure the spectral lines, and you can see whether that galaxy is moving, whether that part of the galaxy is moving toward or away from you. So on a galaxy like this, you would look at this side of the galaxy, and then you'd look at this side of the galaxy, and you assume it's kind of a spiral-ish sort of structure, and you see whether the light is red-shifted or blue-shifted. And this is actually a real data about that galaxy, where the color indicates how much the light is red-shifted or blue-shifted, and what you can see from this picture is that the top part of the galaxy is moving away from us, and the bottom part of the galaxy is moving toward us. And what that implies is that the disk is rotating kind of in that way, where I'm waving my hands at this point and you can't see it, but it's rotating in a way where the one part of the galaxy is moving toward and the other part away. And so using that kind of rotation information, you can work out the rotation curve of the galaxy, which is a plot of the orbital speed versus the distance from the center of an orbit. This is an animation, and I don't know how to make it play in this in a non sort of full screen kind of way. Um, so yeah, let me see if I can get this to play. Yes. Okay, so anyway, in something like our solar system, we can draw a rotation curve for that, where the orbital speed goes down as a function of radius. So if you're close to the center of the solar system, like Mercury, then you're going around really quickly. If you're close to the outside of the solar system, like Neptune, then you're going around really slowly, and you can see that in this animation. And so the key thing about a solar system is that most of the matter is contained in the sun, the star in the center, and so the the mass contained within, the orbit of each planet is really dominated by that center thing. And so as you go farther out, the velocity at which you're moving around goes down. So Vera Rubin was looking at the at galaxies to see how the rotation of how the rotation of galaxies changes as you go farther out. I'm trying to see if I can change the size of this thing. No. Okay. Anyway, so she was looking at galaxies to see how that changes. And so if you look at a star sort of close to the center of the galaxy, or a bit of gas, and then you look at pieces of the galaxy as you go farther out, and then you plot that all together, what you see is that the velocity, the rotational velocity, actually sort of flattens out. So as you go farther out in the galaxy, instead of the velocity going down as you would expect with something where the mass is dominated by by an object in the center, you see that the rotation curve just stays flat, and that's really unexpected because when we look at galaxies, when we look at the light from all of the stars and gas in the galaxies, we expect that all of the mass in the galaxy is really very strongly concentrated in the center. And when you get out to the sort of the outermost parts of the galaxy, they should really be dominated by the gravity of the stuff in the bulge in the very center of the galaxy, and and so they should have this nice Keplerian rotation curve. And so I'm going to see if I can get this to play. No. Okay, so this is another animation that I cannot make play. It's a simulation of what rotation looks like for a solar system and for a galaxy. And basically, with the solar system, the things closer in are moving faster, and the things farther out are moving slower. With the galaxy, everything is moving around in the same speed, which means that the stuff in the center is going around more quickly, and then is making an orbit more quickly, but the stuff at the outside is moving at the same velocity, and it just takes longer because it's going farther. I have other movies in this thing. This is going to be complicated. I apologize for the technical difficulties. Anyway, so we can actually use that property and some Newtonian mechanics to figure out where the mass should be distributed if you have this weird behavior where the rotation curves flatten out. And basically, what you do is you take the outward and inward forces. So with Newtonian mechanics, you have centripetal force, which is mv squared over r, and you have a gravitational force, which is gm m over r squared, where m is the bigger mass, the thing that you're orbiting around, and little m is the small mass, the thing that's orbiting. And you can solve that to get this this equation that relates the velocity at which something is moving to the distance and the mass contained within that radius. So applying that to the galaxy and solar system situations, For the solar system, we see that the velocity varies as 1 over the square root of r, and that's that Keplerian rotation curve. And so if you apply this this equation, then you see that the mass as a function of radius is roughly constant. Basically, most of the mass is in the sun. For a galaxy, the velocity seems to be about constant as you go out. And so if you put that into this equation, you see that the mass as a function of radius is increasing as you go outward. And that's a really strange thing if all the mass is in the sort of visible light in the galaxy. So what we infer from that is that the mass isn't just in the visible stuff in the galaxy, but it extends in this broad dark matter halo. It's called a halo. It's actually sort of a spherical blob kind of thing, not exactly spherical, but we call that a dark matter halo. And the galaxy is very small compared to the halo. When you measure these velocities, you can look at little bits of gas that are orbiting the galaxy out at very long distances, and those all go at the same speed as well. So you know that the dark matter halo extends far beyond where the light of the galaxy goes. And we get all that from looking at these rotation curves, and that's one of the sort of most compelling pieces of evidence for dark matter messing with the dynamics of galaxies. But there's actually a clue about dark matter even earlier by a guy called Fritz Zwicky. This photo is often used of him because he was known to be a very not sure how to put this. He tended to get into arguments with other people sometimes. I've been told that he was actually a very nice person and very charitable and so on. But he did not suffer fools gladly, I guess is a way to put it. So it's common for him to be referred to as curmudgeonly or something like that. But anyway, I'm sure he was a very nice person. So in 1937, which is many years before Vera Rubin looked at rotation curves, Fritz Zwicky was looking at movements of galaxies and movements of galaxies in the Coma cluster of galaxies. And what he found was that the movements of galaxies in clusters of galaxies also implied that there was more mass than we saw, than we could see with visible mass. And we actually have a slightly better way of looking at galaxy clusters now to see where the influence of dark matter, which is to look at the hot gas in galaxy clusters. So this is an image of a galaxy cluster called Abell 1689. Lots and lots of galaxies in there. All of those little blobs are galaxies. And there's also quite a lot of hot gas in galaxy clusters. This is called the intra-cluster medium. And it's a sort of hot ionized gas that glows in X-ray radiation. And it turns out that 80 to 90% of the visible mass in galaxy clusters is actually this hot gas in between the galaxies themselves. And we can look at that hot gas and learn something about how much mass is in that cluster based on what that gas is doing. So basically, you use something called hydrostatic equilibrium, which is the idea that the pressure from this gas is balanced by gravity. The gas is hot and it's glowing and it's pushing out with its own pressure, and the gravity is what holds it in. And so if you can measure how much gas there is and how hot it is, then you can figure out how much gravity you need to hold all that gas in. And what we find is that when we measure all that, we find that about 90% of the cluster's total mass is dark. So, just to reiterate, 80 to 90% of the visible mass is in this hot gas that you can only see with X-rays, and then 90% of the total mass is completely dark and you can't see it at all. And you can only infer that it's there by looking at how that hot mass is being held in. So that's one of the tools we can use. Another tool that we use to see dark matter is called gravitational lensing. And so this is based on the fact that if you look at gravity in terms of general relativity, you find that mass curves spacetime. So this is a little picture of a massive object curving spacetime, and keep in mind this is like one dimension down. So in reality, massive things curve spacetime, which is itself sort of three-dimensional space plus one dimension of time. It's not easy to picture, so we always draw these sort of two-dimensional sheets with a ball on top. So anyway, so mass bends space-time, and then light rays, as they're moving through space-time, tend to follow the straightest, shortest path, which means that the light can bend around the massive object. So if we're sitting over here, looking at this, looking at a source of light that's on the other side of some massive object, then that light source is putting out light rays that are sort of bending around a massive object, and so when we look toward that massive object, we'll see light coming from two different directions on either side of it, and the amount of deflection of those light rays tells us something about the total mass in that massive object. So we can see this with something called strong gravitational lensing, and this is an image of a galaxy cluster with strong gravitational lensing happening, where there's a galaxy cluster with these massive galaxies and dark matter inside, and then behind these clusters are little galaxies, little very distant galaxies, and the light from those is distorted and shows up as these arcs stretching around the galaxy clusters. And so you can see this little blue galaxy on the bottom, or this red streak near the middle. Those are the images of distant galaxies whose light is being bent around these massive galaxy clusters. And so using the fact that mass bends light, and we know how much bending is happening because we can see these giant arcs, we can then infer the amount of mass in these galaxy clusters. And what we see is that it's a lot more mass than you get just by counting up all of the gas and galaxy, stars and things in the galaxy clusters. There's another kind of weak lensing called kind of gravitational lensing called weak lensing, and weak lensing is a way of sort of adding up all the little deflections that light ray experiences when it's crossing the universe. So basically, if you have a number of galaxies in the background of some object, and you look at the shapes of those galaxies, they're going to be slightly distorted by the presence of massive objects. So in these pictures on the left, you have just a simulation of like a number of little dots representing galaxies, and on the right you see how they could be, the shapes of those dots could be distorted by gravitational lensing, by the fact that there's some mass between you and those objects. And here's another simulation where, in this case, you have a massive thing in the bottom left corner, and you get these sort of giant arc strong lensing effects. But if you go some distance away from that, and you look at the shapes and orientations of galaxies there, the orientations of galaxies should be basically random. So if you have disk galaxies, they should look at like ellipses that are kind of randomly oriented. But in this case, because of the influence of the big massive thing in the corner, more of those galaxies are going to be aligned tangentially to the big massive thing. So on average, you're going to have a little bit more of the galaxies being kind of tilted at this diagonal than you would otherwise have. And so it's this statistical effect, and you don't get you can't measure very precisely where all the matter is, but you can get a sort of picture of the broad distribution of dark matter. And you can, when you do that, you can kind of map out where the dark matter is, where all the matter is, because you're really just measuring all of the mass. And so this is a picture of a galaxy cluster, where on the left you see the visible light picture from the Hubble Space Telescope, and you can see again a couple of these arcs from the strong lensing, but also using weak lensing, you can map out where the dark matter is. And in this case, they've drawn on the dark matter as sort of this bluish glow, and it shows that the dark matter is kind of concentrated where the galaxies are. So dark matter and galaxies, luminous matter attract each other because they all have mass. And what we find is that in all objects of sort of galaxy size or greater, the mass tends to be dominated by dark matter. So there's a question of since regular matter and dark matter attract each other, whenever we see the effects of dark matter, we also see regular matter. And some have suggested, well, maybe there's no dark matter. Maybe this is just that regular matter has stronger gravity than we expect. Basically, if we see that the stars in the outermost regions of galaxies are moving faster than we thought, maybe it's not that there's this massive halo of dark matter. Maybe it's just that all of the mass interior to that is pulling harder than we thought. And it's actually difficult to disentangle these possibilities, because if the dark matter and luminous matter are always in the same place, it's kind of hard to say that it's actually a new thing that happens to be coincident, rather than just the luminous matter is acting differently, that gravitational, our understanding of gravity is wrong. And one of the most popular hypotheses for this, this idea that it's just an effect of gravity being misunderstood is something called MOND, or modified Newtonian dynamics, and so for the most part, that there are a number of problems with that theory, and there are a lot of people, most people kind of don't believe it, but there are some people who still say that they think that MOND is a reasonable thing to think about. But I think that one of the most compelling pieces of evidence against MOND is a cluster called the bullet cluster. And the bullet cluster is a situation where you don't have that problem where the dark matter and the luminous matter are in the same place, because you have a collision of galaxy clusters that have kind of moved the dark matter and the luminous matter apart. So this is a picture of the bullet cluster. It's actually two galaxy clusters. There's one over here. It's the bigger cluster. And there's one over here, smaller cluster. You guys can see my pointer, I hope. I can't hear you if you say no, but anyway, I assume that you can see my pointer as I'm sharing the screen. Anyway, so there's a big cluster and a little cluster, and the theory is that those two clusters have very recently collided and passed through each other. So when two galaxy clusters collide, the galaxies themselves are all pretty far apart, so the galaxies themselves don't tend to collide. So the clusters kind of pass through each other, but the hot gas in the galaxy clusters does collide because it's sort of filling that whole space. So when we look in the X-ray at these galaxy clusters, what we see is that the hot gas is more or less concentrated in the center, and we see this shockwave pattern, which suggests that the little cluster has kind of punched through the big cluster, and the gas in the little cluster was shocked as it went through. And so although the clusters of galaxies are kind of off to the sides, the luminous X-ray gas got stuck in the center. And as I mentioned before, the X-ray gas is like 90% of the mass, the luminous mass in galaxy clusters. So if we use this information to try to figure out where the mass should be in these galaxy clusters, we would expect that the mass would all be kind of concentrated around the center, because that's where the hot gas is. So a few years ago, somebody looked at this cluster with weak lensing to see where the mass actually was, and they found that it was not in the center where the hot gas was. It was actually clustered around where the galaxies were. So this is an image of the result of the weak lensing observation kind of painted on. So the blue there represents where most of the mass is in these clusters, And if you flip between the hot gas and the gravitational mass, you see that there really is a significant separation. So if it was the case that that the mass, the regular matter, that luminous matter, was just had stronger gravity, then there's no reason that the gravitational effect should be strongest so far separated from where most of the luminous mass is. So if you put it all together, you can see that there really is that separation. And what you've done is you've really found a way to draw apart the luminous mass from the dark mass. And so you have on the edges of this cluster after the collision, you have the little sprinkling of mass that is the galaxies plus the dark matter, and then in the center you have this hot gas. And so there's really no way to do this with just altering gravity, because if you just altered gravity, the bulk of the mass should really line up with the hot gas. So this is considered to be the smoking gun of dark matter being a real and separate component of the universe, something that really is a massive thing, and not just that we've misunderstood gravity. So this is a movie of what we think that collision looked like. So the blue is the dark matter and the red is the hot gas. And so you can see the little cluster is punching through the big cluster, and the hot gas is getting kind of stuck in the center, and the dark matter is passing right through on the sides, because, as I mentioned, dark matter doesn't care about passing through things. It goes right through like a ghost, and it sort of just sails on past. So I hope that is convincing that dark matter probably is, yes, a really true separate thing in the universe. But that said, we still have no idea what it is. The most likely scenario is that it's something called a weakly interacting massive particle, or WIMP. A WIMP is a new fundamental particle that was proposed in the supersymmetric model, which is an extension of the standard model of particle physics. We don't know if supersymmetry is true or not. We're still kind of trying to figure that out. But if it is, then it might be where we find this new particle. A weakly interacting massive particle interacts only through gravity and the weak force, and has a very sort of small cross-section to interact with anything, even by the weak force. So it interacts very, very rarely and very weakly, but if it does, it's by the weak force. And it might be its own antiparticle, which means that when you get a whole lot of dark matter together, then individual particles of dark matter can collide and annihilate with each other. So you can look for the effects of dark matter with a number of things, and I'll talk very briefly about each of these. There's direct detection, indirect detection, and collider experiments. And these are looking at sort of different ways that dark matter could interact with regular matter using this weak force interaction that dark matter might have if it is, in fact, a WIMP particle. Just to give you some context, the supersymmetric model of particle physics is this idea that that each of the standard model particles, like the quarks and the leptons, neutrinos, electron, things like that, have supersymmetric partners. So they have these more massive partner particles that are similar to them in some ways, but have sort of opposite properties in some other ways. And I don't really have time to go into all of supersymmetry, but basically it involves a new particle called the neutralino, usually, which could be the dark matter particle. And so there are good theoretical motivations for supersymmetry, but we really haven't seen any evidence for it yet, even though we are looking very hard with things like the LHC. But for the moment, a lot of experiments kind of just assume that dark matter is probably some kind of supersymmetric WIMP and look for the effects of that because it is kind of the most well-motivated particle. So for direct detection of dark matter, what we basically do is we take a big tank of stuff, often it's something like xenon, and you sit there and wait for a dark matter particle to come through your tank and bump into one of the nuclei in your detector. So usually you take your detector and you put it way deep underground, underneath a mountain or in a mine or something like that, and you pile on lots and lots of shielding, and all of that is to keep you from getting bombarded by cosmic rays. So ordinarily we have energetic particles from space bumping into things on Earth all the time. And so if you put your detector in the bottom of a mine or under a mountain, then you really cut down that background. So in that case, then the only things that are able to come through are things that really, really rarely interact with any other matter, like things like dark matter particles. And so every once in a while, very rarely, a dark matter particle might come through and bump into one of your nuclei, and you get something called nuclear recoil, which is basically just saying that the nucleus got bumped and moved, and that bumping can create ionization or heat or some kind of light signal, and you look for that with detectors. And so there are a number of these experiments out there that are looking for dark matter through that direct detection method. And there's been a number of possible detections. There are a number of experiments that say we saw something that looks like dark matter. The one that's seen the most, the biggest signal is something called DAMA/Libra. It's an experiment in Italy where they don't have very good background mitigation. So they see a lot of background effects, but they also see something that looks like a little modulation on top of their background, and that modulation they say might be due to dark matter. The reason that you would have a modulation is that, well, okay, so there's a diagram up at the top here. The sun is moving through the galaxy, and the sun is moving at about 220 kilometers per second through the galaxy in one direction, and the Earth is going around the sun. And when the Earth is moving kind of in the same direction as the sun, then it's moving more quickly through the dark matter. And when it's moving in the opposite direction as the motion of the sun, it's moving more slowly through the dark matter. Basically, it's either got the sort of wind, it's either going into the wind or away from the wind at different times of year. And what the DAMA experiment sees is they see that their signal is a little bit stronger in the summertime when the sun should be moving toward the dark matter wind, so into the wind, and it's moving, and they get a little bit less of a signal in the winter when the dark matter should be moving away from the wind, and so have less of a flux of dark matter particles. So, you know, there are a lot of things that might modulate seasonally. There are a lot of reasons why you might have some kind of background that has a stronger signal in one season than another. So it's not really clear that it is dark matter, although they've done a lot of checks to look for other systematic effects, and they haven't figured out what it could be. So I don't know. Nobody really knows what to do with that experiment. They see a very consistent signal, but nobody's been able to reproduce it, and a lot of experiments have seemed to rule it out. So that's a little bit unclear. And then there are a couple other experiments. There's one called CDMS that's seen a few events that seems to be compatible with low-energy dark matter particles. Not really clear if those are real or not. And then there's a COGEN experiment, which also sees a possible detection of something similar with a modulation signal. But again, these are all in tension with other data. And here's an illustration of that tension. So these colored-in regions are regions where experiments think they've seen a signal. So you have the DAMA experiment in yellow, COGEN in brown, CDMS is in blue there, and then CREST, another experiment that's seen something, is in purple. And this is in the space of the cross-section for scattering with a nucleus versus the mass of the particle. And then these sort of curved lines are exclusion limits that exclude everything up and to the right. And you see that a bunch of the experiments are excluding all of the signals that have been seen. And it actually just got even worse for those experiments a couple of days ago when the LUX collaboration, the Large Underground Xenon experiment, released their first data and found that they ruled out those signals really, really strongly. So in the little inset image here, the kind of the X and the little kind of pinkish dots, those are around where the other experiments thought they saw their signal, and the blue line is ruling out all of those detections really strongly. And again, in the bigger part of the picture, you can see that they have this very strong exclusion limit. So they didn't see anything, and they should have seen thousands of events if those signals were real. So it's still a little bit complicated, but it looks like we haven't seen anything with direct detection. Indirect detection is a way to look for the result of annihilation of dark matter particles. So when two dark matter particles come together and annihilate, they might make other particles that are visible particles that can interact with standard model particles and make things like positrons or protons or antiprotons or gamma rays. And we've been looking for those things as well. And so far we haven't seen, we have some limits for what we would see if we had gamma rays coming from concentrations of dark matter, for instance, in the galactic center or in little galaxies around the galaxy, and we haven't seen any really significant signals from small galaxies nearby. We see some weird stuff in the galaxy, in the center of the galaxy, but we're not really sure what it is. There's a lot of things going on in the center of the galaxy, so whether some gamma rays we see from the center of the galaxy are coming from dark matter annihilation or not is really hard to tell. And we've also seen something that could be a hint, which is the AMS experiment, which is a big box stuck to the outside of the International Space Station. They're looking for positrons, and they see in excess of positrons at high energies that they say is consistent with dark matter annihilation. On the other hand, there are lots of things that make positrons. Pulsars make positrons, and that signal is also consistent with just a couple of pulsars nearby producing lots of positrons, and maybe we're picking up the signals from the pulsars. So we don't really know what to make of that either. It could be a signal of dark matter, although the model of dark matter you would need to explain it with dark matter is kind of a very complicated model, but it also could be some kind of unaccounted for astrophysical process. It gets really difficult to disentangle these because you're looking for a very small signal and you're looking for something that could be mimicked by a lot of other kinds of physics. Then the third way to look for dark matter is just by making it yourself. So this little diagram here is a kind of schematic of some possibilities for what you can do with dark matter. I mentioned that two dark matter particles can collide and make standard model particles through annihilation. And I also talked about direct detection, where a dark matter particle and a standard model particle come together, and the dark matter particle bounces off the standard model particle, and you see that recoil. If you kind of flip it around, you can try and take two standard model particles, bounce them together, and annihilate them to make dark matter. So that's what they're trying to do with the Large Hadron Collider. There are a couple of experiments looking for signs of missing energy in collisions, where they would have a collision and they would count up all of the results of that collision and they would see something missing. And that missing thing could be a dark matter particle that just flew right through the detector and didn't leave a trace. So that search is ongoing, and so far they haven't seen anything, but when the LHC turns on again in, I don't know, a year or something, hopefully we'll get closer to figuring it out with that. And then there are future experiments that might also contribute a lot to that. So there are a lot of things to look for. But basically, as things stand right now, we are pretty sure that dark matter exists. We have no idea what it is. We have some theories, and we don't know if any of those theories are correct. And we have some hints, and we don't know what to make of those hints. None of it is conclusive at the moment. But if we put together the direct detection and the indirect detection, cosmological probes, collider experiments, look for the effects of dark matter in the early universe, which is what I work on. Hopefully in the next few years, we will be able to have a much better idea of what dark matter is, and a much better idea of how it's helped to form all of the matter that we see in the universe now, and what effect it's had on the early universe, and what effect it might be having today. So yeah, so that's where we're at, and so stay tuned. Hopefully we'll know more about this pretty soon. So that's it. So questions?
Dr. Burris and John, if you want to unmute yourself, you can. I can't unmute you.
Hi.
Oh.
Hi.
I'm loud.
Yeah.
Okay, cool.
So, Dr. Burris?
I'm going to keep myself muted because my dogs are in.
Do you want to ask a question on chat, Dr. Burris?
No, I'm good. Thanks. I enjoyed it, though. It was really good.
Cool.
All right, John. You got any questions?
Oh gosh. I don't know. Everything was just so cool. I really like it.
John is our SBS president. He's away now on vacation.
Okay. Well, I'm glad you were able to join us.
Yeah, no, I really wanted to see this. I was really excited for it.
I got it, Shelby. So we're going to turn on the lights just so you can see. We had a really good turnout. There's over 40 people here, plus the people joining us on. So, can you see us?
Yeah, I can see.
Hello. I have to get my face on it. So the one standing up, Becca, will you stand up? Oh yeah. This is our secretary. Her name is Becca. And then
Hello.
Stand up. Oh, that's Sarah. She's our treasurer. And I'm vice president, and John was the one being really loud in the beginning.
Yeah, sorry.
Do you have any questions for her? Okay, go ahead and stand up.
Okay, when you're talking about direct detection of dark matter, you talk about.
Yeah.
I was wondering how, since you said they were like ghost particles, just went right through normal matter. Can you kind of explain how that collision would actually take place?
Yeah. So the idea behind direct detection is that it's, for the most part, dark matter does pass right through things, but very, very rarely, every once in a while, if you get a really direct collision, then you can actually bounce off something. And it's just that those collisions are so rare that on sort of cosmological scales, we would never see an effect of it. And it's only if you watch something really carefully for a really long time and have extremely sensitive detectors that you can see. Something just happened with my. Oh, it came back. Okay, sorry. It's only if you watch for a really long time and you have very, very careful measurements that you can see that recoil. So basically we have limits on the cross section for those collisions in space, in particles in galaxy clusters and galaxies and things like that. And it's possible that there's still some occasional interactions that would show up in our experiments. So it's a matter of it being just a really, really, really rare event.
Gotcha.
Okay, does anybody else have any questions? I know someone else. Okay, go ahead. You can if you want, so she can see you.
When was the idea of dark matter first proposed, and what was like historically the first piece of evidence used to justify its existence?
Sorry, so you were asking when was it first proposed, and what was the other question?
And what piece of evidence was used in the beginning to justify its possibility?
Okay, the first proposal was that proposal by Fritz Zwicky in 1937. He's the one who kind of came up with the idea, and that he was looking at the motions of galaxies in clusters, looking at watching the Doppler shifting as galaxies are moving around in clusters of galaxies, and counting up, how much energy those galaxies have, and looking at how that matches with the amount of mass that you see. But for a long time, his results were kind of not trusted, and part of that is because it was kind of a difficult measurement to make. Part of it was because nobody had a good explanation for why it would look that way, and part of it was probably because he was not always kind of listened to that much, because he made a lot of enemies as he was working on that and a number of other things. So it wasn't until Vera Rubin's observations in the 70s when it really became clear that dark matter was something that we had to deal with, because her observations looking at the rotations of galaxies were very, very solid, and clearly needed some explanation.
Anybody else? Anybody else have a question?
Well, I've got a question. Okay.
So I have massive compact halo objects been ruled out at this point?
Yeah, so I didn't have time to go into that. Before WIMPs were proposed, there was another idea called MACHOs. And MACHO stands for Massive Compact Halo Object. And the idea of MACHOs is that maybe the dark matter is just big things like black holes that happen to be running around in the halo of the galaxy, and those are contributing that extra mass. They are pretty solidly ruled out for the most part. There are a couple of ways that you can rule out MACHOs. One is by looking at something called microlensing, which is where you look for a gravitational lensing effect as a little black hole passes between you and a distant cluster of stars. We have experiments that stare at the galactic center or stare at the Large Magellanic Cloud, that are just looking at a whole bunch of stars and waiting for one of them to flicker as a black hole passes between us and them. And basically they just didn't see enough flickering. They didn't see enough effects to account for all of the mass. So if all of the dark matter were like black holes of the mass of the sun, then we would have seen a lot more of this microlensing. If they were black holes that were, say, 100 or maybe like 10,000 solar masses, those black holes would have other effects. If they were like 10,000 solar masses, they would mess up the shape of the galactic disk, stuff like that. So there are some pretty strong constraints on massive black holes as dark matter, and they pretty much seem to be ruled out. There's one caveat, which is that if dark matter were all made of black holes that were about the mass of like an asteroid, we don't have very good constraints on that. So if you were somehow able to make black holes in the very, very early universe that persisted till today and didn't grow very much, and they were like 10 to the 18 grams or something like that, we'd see very few signs of those. And so that idea is not entirely ruled out, but theoretically it's quite difficult to make those black holes in the early universe. So observationally, there are a few sort of windows where MACHOs could still be important, but theoretically there are a lot sort of a lot more difficult than something like a new stable particle like a WIMP. I think John had a question, he said in the chat thing.
I had to mute it. It was loud. Oh,
So I might have missed it, and I'm sorry if I did. But you talked about MOND, the
Yeah.
modified Newtonian dynamics, I believe,
Yeah.
right?
Yeah.
How is it modified?
So the modification is that they propose that that on certain scales gravity is just stronger for regular mass, and so it's kind of there are a few different sort of theoretical formulations, of MOND that have different ways of modifying the gravity, but basically they're just adding a term to Einstein's equations that makes gravity, the force of gravity, stronger when you're at sort of particular gravitational accelerations. So what it would do is that it wouldn't change the way that like planets orbit the sun, but when you're looking at galactic scales, it would mean that that the force of gravity doesn't just fall off as a proportional to r squared, to 1 over r squared. It actually is stronger when you're looking at very at the sort of weakest regime of gravity.
So you said it was modified. They changed something on Einstein's equations.
Oh, sorry, not on Einstein. I mean, well, they have a couple of formulations. They have one. They have something that's a kind of relativistic version, but MOND, the original MOND, is just changing Newton's equations and just changing that r squared dependence of gravity. That's why it's called modified Newtonian dynamics.
Okay, so they just changed the proportionality, but is it the same gravitational constant, or is it a different one?
Well, they add a term basically. So it's the gravitational force goes down as 1 over r squared, but then it also there's an extra term that's proportional to the mass, I guess, but it only kicks in at certain gravitational accelerations. So I don't remember what it looks like exactly. It's the original MOND is not a consistent theory in terms of it's not consistent if you try and formulate it as a relativistic theory. So there are various problems with getting the equations to work out in different regimes. But there's a relativistic version of MOND called TeVeS, which uses vector and scalar fields in addition to the tensor field of general relativity. It's a little complicated, but yeah, it doesn't seem to work. So, yeah.
Okay, thank you.
You're welcome.
he muted himself.
You talked a little bit about your work in dark matter in the early universe. Could you tell us about that?
Sure. So what I'm interested in, so in general, I've worked a lot in like early universe physics and stuff that's on the border between particle physics and astronomy. And what I'm interested in at the moment is looking at the possibility that dark matter has some kind of particle physics like annihilation or decay or something like that, and seeing how that would affect the first stars and galaxies that form in the universe. So if for instance, the first stars that form in the universe, they form in the centers of dark matter halos. If those dark matter halos have dark matter annihilation happening inside them, then that changes how much heating is happening in that halo. And then when you're trying to form a star, you have to balance that heating, which would create like a pressure term. So there's stuff like that. The same kind of thing happens with the first galaxies, where you have, if dark matter is annihilating, you're getting additional radiation and heating and ionization going on in the universe, and you have to kind of figure out what effects that would have on the first stars and galaxies. And so what I'm trying to do right now is put together a big simulation that that calculates all of those effects and puts in the particle physics of dark matter, and just kind of see how the evolution of galaxies changes if dark matter is doing something interesting like annihilating or decaying. And this is something that hasn't really been done in detail before. People have looked at kind of individual effects of dark matter on different kinds of astrophysical processes, but nobody's really done a full simulation of all of galaxy formation from the first galaxies to today, including dark matter. So that's kind of what I'm trying to do. I'm working with a team of galaxy simulation people at University of Melbourne, and they're putting together a massive simulation of galaxies over billions of years in the universe, and I'm trying to kind of put in the dark matter particle physics.
Does anybody else have a question?
How about one more? So,
Okay.
you're talking with a group of undergraduate students. What sort of advice would you give yourself if you travel back in time and talk to this same group of students? What sort of advice would you give these students?
Okay, so let's see. Well, if what you want to do is go into something like physics research, there are a number of things I would suggest. First one is probably get really good at math. Did something yeah, so
That's a good one.
sorry? Yeah, so one of the big misconceptions I run into a lot is that people think that either you're good at math or you're not good at math, and that's not true. If you practice, if you do a lot of math, you become better at math, and that's true for everybody. So I would suggest that if you're interested in physics and doing a career in physics, but you're worried that maybe you're not, a math genius, do lots of math and become a math genius. And just practice and work at it, and it helps a lot to if you get really good at math, then physics gets a lot easier, and also it's kind of awesome to be really good at math, and you get to do cool things and understand the universe a lot better. So that would be my first suggestion. Aside from that, learn how to code. Computational skills are really, really important in all kinds of physics research these days. It will make your life a heck of a lot easier. If you're good at coding, learn how to do things like version control. That's one of the things that will make you a much better researcher and a better collaborator, and everybody will be happy with that. And then, do what you're passionate about, It helps a lot. It's possible to be a fundamentally very lazy person and yet work really hard if you are passionate and enjoying what you're doing. So I would say that if you're really passionate about physics research or astrophysics or whatever, that's going to help. And find ways to feed that passion and find ways to keep yourself, excited about your work, and that's going to make you a better researcher, and it's going to make things a lot more fun. So I would definitely suggest that. I have a list somewhere of advice for aspiring astrophysicists. I don't have it in front of me right now, but I can send you guys that. There's a bunch of other points on there. But yeah, so that kind of thing. Try not to burn out entirely. Balance work and life. That's important. I don't know, stuff like that. Oh, and try and do research as early as you can. One of the things that I did was I actually got started in research when I was in high school because I was fortunate enough to be close to a university where there were people doing physics research, and I was able to kind of, edge into that. And I didn't do anything important or difficult, but I was able to kind of be around researchers and see what they were doing and see how research works as a pursuit, and that helps a lot, partially because it kind of looks really good on your CV if you've done research, and that helps you get other opportunities, but also because it made it possible for me to see what research is really like and to see if it was something I actually wanted to do with my life. It's good to find that out early, because a lot of times people are, really, really interested in science, but then when they actually do science, they just don't find it that much fun. So if you get started in research early, either as you can do there are a number of sort of official programs that you can get involved in, things through the National Science Foundation or something like that. I'm sure that your professors can hook you up with those kinds of things. But you can also just kind of get in touch with researchers and say, hey, can I sit in on your lab once a week or something and see what you're doing? Usually people are down with that. Usually researchers are really excited if somebody else is interested in what they're doing, because a lot of the times when you're doing research, you're kind of sitting around by yourself and you feel like nobody cares. So if there's a sort of enthusiastic young person coming up to you and saying, I find your work fascinating, we're kind of easily flattered by that kind of thing. So feel free to pester people. Don't stalk people, but to a reasonable degree. And also finding mentors is helpful. Get in touch with people who do the kind of work you want to do and ask them questions. Usually people are pretty open to talking about stuff like that. Yeah, that kind of thing.
I didn't pay her to say that. So that's good. Any other questions?
Is there a difference in the ratio of the density of dark matter around forming galaxies and galaxies that have been stable for long amounts of time? Or?
Sorry, the question was between what kinds of galaxies and
whether there's a difference in the ratio of the density of dark matter around forming galaxies and stable galaxies.
Did you say forming galaxies?
Yes.
Okay, so when a galaxy is first forming versus when it's been around for a long time, yes. What the difference is between the amount of dark matter? I don't think there's a big difference. It's hard to say because we don't have that many observations of exactly how much dark matter is in early universe galaxies. So we have good observations of the dark matter content of nearby galaxies, but most of those are quite evolved, quite recent or old galaxies that have been around for a while. We know that there are some kinds of galaxies that have a higher dark matter content than others. So there are something called dwarf spheroidal galaxies, little galaxies that are nearby, orbiting the Milky Way in some cases. Those galaxies tend to have a much higher dark matter content than, say, spiral galaxies, highly evolved galaxies that are, more sort of gas-rich. And some of that might have to do with little galaxies don't have as much gravity, and so if supernovae and things like that are going off in these little galaxies, they can blow out all their gas and end up with more dark matter than gas. So that might be an issue. But basically, it seems like there are some trends in what kind of dark matter fraction you have between galaxies of different shapes and sizes. But I'm not sure how it varies with galaxy age. I think that's a little bit harder to measure.
Let's let's give Dr. Mack a round. Thank you very much for spending your time with us today. We appreciate it.
You're welcome. Thanks for coming.
Fantastic. Thank you.
Okay.
Bye.
Bye.